Just like data close to the radar can have issues, so can data far from the radar, particularly at distances greater than 50 to 60 miles. This is because the radar beam spreads out the farther it extends from the radar. Think about shining a flashlight in a dark room. The light spreads out and becomes more diffuse the farther it gets from the flashlight itself. The same thing happens with the radar beam. For every 10 miles the beam travels, it spreads out approximately 1,000 feet, so at 120 miles from the radar, the beam is over 2 miles wide. This has significant implications on the resolution of the echoes returned to the radar. Many storm scale features easily seen in data close to the radar, such as hook echoes and boundaries, are often muddled or even fully masked at long distances from the radar. In addition, because Earth's surface is curved, the radar beam gets farther and farther from the ground the more it extends outward from the radar, aside from instances of ducting. At a distance of 100 miles from a radar site, the beam is about 10,000 feet above the surface, and at a range of 200 miles, it's about 29,000 feet above the surface. Therefore, the beam overshoots the lower portions of storms at long distances from the radar, making the analysis of low-level features like mesocyclones, tornadoes, and boundaries nearly impossible. This is especially the case in radar holes, which are areas that feature little to no low-level coverage from any radar. This map shows the radar coverage at 4, 6, and 10,000 feet above ground level, indicated by the yellow, gold, and blue shading respectively. Areas in white receive no radar coverage below 10,000 feet. You can see that several areas that frequently experience severe weather lack robust low-level radar coverage, including parts of New Mexico, Texas, southeast Oklahoma, Nebraska, and the Dakotas. Unfortunately, these issues are without a viable solution aside from adding more radars.
Join our channel membership and unlock extra videos, live group coaching, and unlimited Q&A.
For example, let's look at the supercell that produced the Barnsdall, Oklahoma EF4 tornado on May 6, 2024, using two different radar sites. First, we'll look at the supercell from the Tulsa radar site KINX, located about 40 miles from the storm. Note the well-defined hook echo and rear flank downdraft gust front boundary, evident in both reflectivity and velocity data, as well as the strong tornado vortex signature. Now let's switch to the Oklahoma City radar KTLX, located about 90 miles from the storm. The aforementioned features are no longer evident, and the storm looks a lot more amorphous. This is a result of the beam spreading out significantly at this range compared to that of the Tulsa radar, degrading data resolution. Also, the velocity couplet is a bit broader as well. In this case, the beam was about 9,400 feet above the surface, so we're only getting a look at the mid-level mesocyclone and are unable to make any clear determinations about any tornadic activity from just the reflectivity and velocity data. Intense tornadoes can loft debris tens of thousands of feet into the atmosphere, so in these situations, correlation coefficient may still be helpful.
Remember to check out those links in the description below, and then watch another video.